Yay. And you may again notice that this is a pretty sizable class, which is great, but don't feel overwhelmed. Um, so I actually was once sitting in a lecture. This is my personal embarrassing moment, which you guys will, because you can turn your cameras off, you will never have to experience. I was once sitting in a lecture hall of 200 and something students as a junior in college, and it was raining outside and it was kind of warm in the room, and I was having trouble staying awake and fell asleep. And I this happened to me from time to time anyway, but apparently all my friends who I was sitting with thought it'd be really hilarious if they didn't bother to wake me up. And the next thing I knew, there's a big puddle of drool on my desk, and I look around and the whole lecture hall is empty.
I'd say you're lucky on that one, Scott. We're supposed to draw on you when that happens.
Yeah, I know. But the concept of a 250 student lecture hall clearing out and you not noticing anything. All I can say is I must have been tired. So,
Guy's got to get his rest.
yeah, just it should have been the night before. I also had a habit of sleep of sitting right in the front row thinking that that would keep me from falling asleep. Because of the humiliation that I knew that I would experience by falling asleep right in front of the professor. Nope. Just meant he had a bird's eye view of me falling asleep right in front of him. It's almost 9 o'clock, and I assume people are going to continue to trickle in. And I'm looking at my email, and I hope nobody's sending me a note that says I can't get into the Zoom meeting. So I haven't gotten any of those yet. It's 9 o'clock, so let's start. Um, Good morning. My name is Scott. My call sign is N7JI. I'm in Eugene, Oregon. And welcome to our May 25th through 27th technician license exam class. And a little bit about myself. I've kind of almost lost count. This is something like the 38th or 39th time that I've taught a license class for a technician class or general. I have done a couple of general classes. Um, they typically take a little bit more preparation and a little more time, and I don't mind that. I just, with my work schedule and life schedule, I have to try to optimize the use of my time. And I find that if I can get 25 new people licensed, I am doing a good thing. So this is what I choose to do with my vacation. Sometimes I'll do it on a weekend. This happens to be spring break. And so it's spring break for both of my kids, one of whom just actually took the bus to Portland, and the other one who is in college at the U of O. So neither one of them is actually even home right now. So it was, I guess, a good plan to go ahead and teach a class over spring break because I'm not bothering anyone. My wife is still asleep. Um, so a little bit about me. I've been licensed since I was 15 years old, and you may ask, why is doing something like this important to me? So much so that I would, say, oh, you know what? For my spring break, I'm going to take some vacation days and I'm going to teach a license class. The reason being that this is actually really important to me. That ham radio has given me a lot over my life since I was 15 years old. It's given me friends. It's given me lots of practical hands-on experience with things that I never would have experienced, even in engineering school. I do happen to be an electrical engineer. I have a master's in electrical engineering, and I focused on communications and electrophysics. Oddly enough, that's not what I do for work and never has been what I do for work. For work, I build factory automation equipment. So still engineering, still electrical, but more on the programming and power and sensors side of things rather than RF. So I get to do RF for fun. And let's see. Other than that, I have never gone through a serious period of inactivity. If I hide my photo right here, you will see both of my kids. My kids are now 20, 21 and 15. Um, my 21-year-old is Hannah. She's W7HER. She has an extra class license. She's the president of the University of Oregon Club and has been since its inception 3 years ago. And my son Nate is K7NAR, who's on his way to Portland today. He has his general class license and has had it since he was 12. My daughter Hannah, I will also say, is also a volunteer examiner, and it is quite likely that she will be present during the examination session on Thursday if you're signed up for that. So they like to say that they really didn't have a choice as to whether or not they got their licenses. There's a photo that I have, and I don't think I have it right here, but of Hannah basically eating my microphone during sweepstakes in 2001, no, 2002, when she was 6 months old. Sweepstakes is a big on-air contest, and so she was gnawing on my microphone while I was holding her in my lap. So she really didn't stand a chance. And I kind of challenged her to get her license, and she was in a freshman physics class, and she said, okay, fine. And then when COVID hit, I said, well, you got 2 more months of school that you're not going to have. I'll give you $100 to get your general exam, to get your general license. And she said, fine. So she went and did it. I said, okay, fine. I'll give you $200 to get your extra class license. And she said, okay. So she did. And then she became a volunteer examiner and so on and so forth. And one of the cool things about this is that if you happen to be a student and you have a ham radio license, you are eligible for all kinds of scholarships. And she received scholarships to go to the U of O from radio every year that she was licensed. So that's all 4 years of college. So if you happen to be a student and you have a ham radio license, apply for those scholarships. So let's see, as far as what I like to do on the air, let's see. I do a lot of Morse code. I teach Morse code. I still use Morse code, and it's still my favorite thing to do, even though you don't have to learn it anymore. I've actually found that more people want to learn it than have ever wanted to learn it before. When about 10 years ago, I was the founder of the station that we have over here at the Eugene Science Center, which has gone through a serious upgrade during COVID as a result of a grant that we received to upgrade the station. We actually have several Morse code keys there. And what do we find? We find that kids who come through, yeah, the radio's cool, but they really like to pound out Morse code. It's something different that they don't normally get to do. So we're there. I like to work with kids. I like to teach. I also like to operate. I'm a contester. I've always been competitive. Contesting is the radio sport side of ham radio, which is competition. You get on the air, you work as many people as you can in as short a period of time in a given period of time. And I really enjoy that. I like DXing, which is working long distance. And I also enjoy working very, very low power contacts. And Gary there is one of my co-conspirators. Say hi, Gary. So Gary and I are going to be co-teaching a class at the YMCA in April and May. And one of the things that we like to do is antenna experimentation. And we'll get to that and why that is true in a little while. And okay, so Nicole, you had a question, but that was a long time ago. And do we have any questions before we get started?
Scott, I just have one. Hopefully it won't take a second.
Yep.
It's gnawing at me, so it's probably smart to ask it up front. I signed up for the test on Thursday, but it says Anchorage.
Yep.
Is that the correct thing?
Uh-huh.
Okay. That's what it said.
Anchorage, Anchorage ARC Anchorage ARC.
Okay, good, thanks.
Okay, so. Okay, let's see if I can do this. What is this doing? I don't understand this at all. Ooh, okay. Yes, I understand what that, I don't understand what that was doing. Let me try the whiteboard again. And okay. Owner of the whiteboard only allows sharing with users within the same organization. Yes, we'll be recording. And yes, my whiteboard is now doing strange things that I don't understand. Okay.
And just close that dialogue.
Which one? Notice it says Steve
The owner of
C.
the
and Gary
whiteboard. The owner of the whiteboard, just close that.
right there.
Oh.
No,
never
that
mind.
didn't do it. I wanted the old school whiteboard, and now it's always defaulting to the new one.
He wants
This
you to
was-
close the message box.
I don't understand what this thing is doing now. Oh, that's fun. I want the old school whiteboard. Sorry, folks. I don't know what this is doing. You know what? I said I wanted the old whiteboard. Darn it.
Scott, I thought you played with your toys a lot more often.
I did. You know what? I said whiteboard, and there's whiteboard. And the owner of the whiteboard only allows sharing. Okay. Let me try something here.
Obviously, you didn't read your email about
I
checking your
did. I
early.
did. I actually checked it like 10 minutes ago and it was working fine. Security.
That's like I logged into Zoom at 8 o'clock this morning and it was working fine. I go to log in to come into class
Yeah,
and it said I needed an update and kicked me right out and updated itself.
there you go.
That's question number 10 under Murphy's Law.
That's right. Okay, let me start this again. Did it just kick me out? It kicked me out. Oh, that's fun. Okay. Well, give me a second here.
Says, I just went to whiteboards and it says host disabled participant whiteboarding.
Yes.
Yeah.
So let's see if that works. I just did that. Okay, we're going to try this again. And I swear I just tested this a little while ago and it worked fine. Okay. Make co-host. Wow, that's embarrassing. Why is it doing this? Does everybody see that?
I see it.
What the heck is that?
You're playing
Just
Tetris.
start drawing over it. We're all bouncing around the screen, whatever.
It's
We'll
not
get the
even
point.
letting me.
Have you tried clicking out of the dialog box to see if you can get access to this stuff on there?
Which dialog box? I don't even know what to click.
When you get the little warning, there's a little X in the right-hand corner where it says the owner of the whiteboard.
Wow.
Yeah, those are per participant.
Yeah, I see all these participants and
Yeah, you have like 60 backseat drivers.
yeah. What the heck? Okay, like I can do that. That's smart drawing.
Is it a presentation?
Well, no. I just want a plain old stupid whiteboard that I normally use.
Does
Huh.
everybody need to click on that dialog box?
No, they shouldn't. Let's see.
No, it's all in Scott's.
Yeah,
control.
this is all on my thing. It's all on my thing and it's on an iPad.
It's just Scott being special.
This is crazy. And I even shut it down and started it again. And okay. All right.
Just adapt
What?
and overcome. Just work with what we
What?
got.
No, I can't. I can't even grab control of it.
Ah,
Everyone who has access to this, I don't understand this at all.
Okay,
I don't have it.
on my board, on my screen, it says the owner of the whiteboard only allows sharing with users within the same organization.
Right. Yeah, I have that too.
I can close it. And then
Yeah,
at the top, it says sign in now to avoid losing access to whiteboard after meeting.
nah, hold on. Let me click on whiteboards here. Unbelievable. And you know, I tried this presenting. There we go, maybe. Okay, now I have to figure out how to get a pen.
There, I see your name only now.
Yeah, but now
There we
the
go.
thing is that my whiteboard pen does not seem to work.
Huh.
Oh my God. See, I have this,
Yeah, I see a squiggle.
which is, but I have a stylus, but it's not working.
I see a, looks like you drew something.
I don't understand this at all. Okay, anyway. So what we're going to do is I'm going to try to do this. And I'm going to do it with my mouse. Okay, because Zoom sucks apparently today.
I think the squiggle worked.
And look, now it's showing up with everybody again. It makes you think that somebody's taking control of it from like outside, you know? Well, this is really embarrassing. My apologies, but I really did try this. I don't want to collaborate. Sorry, I don't want to collaborate. Nothing personal, everybody.
So, hey, Scott, if
Yeah.
you, the three white lines next to view only there in the upper left, click on that, click on view.
I don't
You
even
can,
right there.
so you click on view and then you can turn off collaborator cursors.
Okay. Now, what I really want is to get my old school. Start this whiteboard preferences view.
Not,
Export.
yeah,
On my screen, I see a dialogue says you are following Scott Rosenfeld.
Yeah.
You are viewing Scott Rosenfeld.
and that's what I have as well.
Stupid, stupid computer. Okay, so we're going to do it like this. I am going to, oh, great. Now we're going to try it again. I hope it doesn't go back to the way it was. Whiteboard, new whiteboard. Okay, well, at least that didn't come up with all the problems. Okay, good. All right, so we're going to learn how to do this in a little different way, and then I'll try to figure it out in my spare time. Okay, sorry for the hiccup there, everybody. That's what happens when Zoom decides they're going to update something without really telling anyone, because I specifically said we're going to use old school whiteboards, not new school whiteboards. Okay, so what we're going to do is we're going to draw a circle. All right, we're going to draw a circle, and we're going to draw this, and we're going to draw this. So now this is a circle where we're going to have 4 quadrants. How many degrees are in a circle, everybody?
60.
360. So this is our 0, this is our 90 degrees, and we're going to wrap around this way. So we start at the horizontal right side axis, and we start adding degrees going up and around in a counterclockwise fashion. So we have 180 degrees over here. And we have 270 down here. And when we get back to 0, that has another name. That is 360 degrees, right? We can call it 2 different things. We could actually call it more different things than that. We can make it 360. We can actually go negative 360. We could go 720 and so on and so forth. So we have many different names for that point. So if it seems like we're starting off with a little bit of trigonometry, well, okay, well, it is, because we are starting off with a little bit of trigonometry. So we have 2 functions here. One of them is our altitude above ground, and another one is our distance left and right. Our altitude above ground, that's in the positive direction. Our distance to the right is considered in the positive direction from this point, which is the origin right in the middle. And as we go up and down, this is related to how far out we are on this circle. This is a radius of the circle. And the distance up is a function of the angle at which we have moved. Going up and down, this is known as the sine. And going left and right, this is known as the cosine. So for those of you who have done for those of you who have done trigonometry recently, this is going to be very fresh in your mind. For those of you who haven't, or it's been 50 years since you did it in high school, what you'll find is that maybe it doesn't make a lot of sense, but that's okay. This is what you probably learned in high school and have forgotten. So often we put an E after sine and we make it S-I-N-E. So the distance up and down is called the sine of the angle. And this, for a unit circle, a unit means that it's a radius of 1. So we're going to make our radius 1 unit. What is the highest up above ground that we can get? That would be 1. And how about the farthest below ground that we can get? We can go 1 unit down below ground. We can also go 1 unit over here and 1 unit over here. So this unit circle has limits on the sine and cosine of 1 and -1. So as those numbers change, what we end up having is a plot that we can say, okay, we're going to make a graph right here. We're going to start at 0 degrees and we're going to go to 360 degrees over here. And as we get, let's say we're going to do a plot of the sine. As we go from 0 degrees to 360, where are we going to be at the top point?
We're 90 degrees.
90 degrees. So that's a mark right here. We're going to put our 180 and then our 90, and we're going to do this. So we're going to be at our peak way up here at 90 degrees. And how about at 180? We're going to be back down at 0. And then at 270, we're going to be at -1. And now we're going to play connect the dots and tell me if anyone recognizes this curve.
Sine wave.
That is a sine wave, more or less. It's not pretty, but that's a sine wave. So what that means is that a sine wave is actually made by, let's say that you're sitting on a merry-go-round. This is our merry-go-round right here. This is our merry-go-round, and you are sitting at one specific point on the merry-go-round. The path that you trace, if somebody were to say, how far left or right, or how far up and down are you going? The path that you trace out looks like that. It makes a sine wave. And that is why also, let's say that we're looking at what the seasons look like and things like that. Anything that is rotating makes waves that follow the path of a sine wave. Now, what are some interesting things that you could do with this sine wave? So we're gonna we're going to clear off this drawing. What could you do with that sine wave? How are some ways that you could change it? Everyone, what do you think?
Change the unit?
We could change the unit. We could make it bigger or smaller, right? And that would mean that the circle that we're writing on is bigger. And the size of the sine wave has a name. And that's known as our amplitude. And what's another thing we could do with it?
Trough.
What was that?
Trough.
Say that again. You broke up a little.
Your trough?
Yeah, okay. Well, let's look at it like this. We could shift the whole thing up. We could do an offset so that it's like that. What else could we do with it?
Move it forward.
You could move it, which way is forward? To the right or to the left?
Say to the right.
Okay, we could make it and shift it like this. Or we could shift it like this. What else could we do with it? Could we make another one and do this with it?
Yeah, you can shorten the wavelength.
Yeah, well, you can increase the frequency. So
Exactly.
Yep. So what we're doing now is we are figuring out different ways to modify what we started with. So we started with a plain old circle and a merry-go-round going around like that, and you being the unlucky rider sitting right there. Please don't throw up. As this speeds up, as the merry-go-round speeds up, what happens to that graph? What happens to the graph as we speed up?
Increased cycle.
Can everybody see the whiteboard okay?
Yeah.
Yeah.
Okay.
We can see it.
Okay. So as we speed up, we
It
basically
looks like you do, sorry, looks like
Go
there
ahead.
is somebody who can't see it.
I can't see it.
you can't see it.
No, I've got add a sticky note is all I see.
I think if you enter full screen, you can see it. When you're not in full screen, I don't think you can see the whole whiteboard.
Where's my screen?
Go to the top right of your Zoom. It says view, enter full screen.
Oh yeah, I think you're right.
Oh, there we go.
Thank you. Okay. All right. So what we've done is we have changed the speed at which we go around the circle. And what happens if we were to slow this down a lot? We would basically take our sine wave and potentially stretch it out really far, right? To the point where it's actually completely off the page even. So that is basically, can everyone see okay now?
I can see it just fine, always have been able to. And if they
Okay.
can't see it, they can click on the screen and move it around to where they can adjust it to where they can see where it's at.
Okay.
You can go outside.
Okay.
I have a class. I'm at school right now.
Okay. So basically by changing this, what we have done is we have altered how this sine wave is formed. So now what we're going to do with it, oh, did somebody just draw a square? Okay, so what we can do with this now that we've drawn the sine wave, and there's our circle, and hopefully everybody can see me erasing it. And okay. Now, what we're going to do with this sine wave is we are going to every time we go around, as this merry-go-round is spinning around, we're going to time how long it took to get around the circle. So if it took 3 seconds to get around the circle, we would go 1, 2, 3. That would be known as our period, which is represented by the big letter T. And Rhonda, you still only see add a sticky note? Rhonda? Hello, Rhonda. Everybody practice talking to. Okay, well, I can't hear Rhonda. Okay, so we have our time. That's our period. That's how long it took to get around. That's measured in seconds. So that would be a 3-second period.
Why,
So if-
why is it T?
It's just a big letter T because it's in time.
Okay.
So, and that's just represented with a big letter T. Okay, so now that we have the big letter T for time or period, now we can say we have something else, which is known as the frequency. The frequency is how many times per second something happened. Frequency is defined as 1 divided by the period. So this is in units of something per second. So that could be me clapping. That could be jumping up and down. That could be any number of things per second. So if a bunch of things happen per second, that gives us our frequency, known as a letter F. The unit of something per second has a name, and that is a hertz, named after Heinrich Hertz, who was a foundational character in radio frequency and was a scientist in the 1800s. So if we have a period of 3 seconds, what is our frequency?
Hertz.
It's not 3 hertz because that would mean that you have 3 times per second. If it took 3 seconds to get around, how many times per second does it get around?
1/3.
1/3. So you have a frequency of 1/3 of a hertz. Nobody said it had to be greater than 0. So now let's change this so that we take 1/10 of a second to spin around. And if you're working for NASA, you're probably doing a centrifugal experiment. Let's say that you're sitting in a little car and it's spinning you around to see when you're going to puke or when you're going to black out. So you're spinning around in 1/10 of a second. Okay, so how many times per second would you be spinning around? 1 divided by 1/10 is equal to 10 hertz. 10 times per second. So what this now means is we have related period and frequency. And you may be wondering, why are we relating period and frequency? Well, the reason being that they are completely related because we're going to move on to the next thing. So we now have a period and a frequency of something that is happening. And it doesn't have to be a radio wave or anything like that. It's just some kind of phenomena. So now what we're going to do is say that we are going to take that circle and we're going to stand it on its side. So we have a circle that looks like this, which is not a very well-centered circle. There, we'll put it right there. And we're now going to take that circle and we're going to stand it on its side. Instead of looking at it from the front, like a bicycle wheel, we're going to look at it on its edge. What does it look like on its edge? It looks like a vertical line. Okay, so now as this person or particle or whatever sitting on the wheel as it's spinning around is going around and around and around, what do we see on the bicycle wheel?
Up and down.
It simply goes up and it goes down. And does it go up like at the same rate, or does it change based on where you are? When it's at the top, it doesn't look like it's moving at all, right? When it's
Right.
when it's at the bottom, it doesn't look like it's moving at all.
So its rate changes as the distance of the cosine.
Or the sine, either one.
Yeah.
So if you've ever wondered why during the season, as the seasons change, why we seem to lose so much more sunlight in the fall than we do during the summer days, or we seem to gain sunlight a lot quicker in the spring than in the winter, that's because it is a sine curve. And when we get to the top and the bottom, these are our solstices. And when we are changing rapidly, these are our equinoxes, and the amount of sunlight that we get changes very rapidly because the slope is maximized at those points. So now, as we were to draw this, and we know that it's not moving up and down at the same rate, we're going to add another dimension of movement. So I'm going to add another color here. We're going to move it this way at a certain speed. So we have a frequency up and down, or speed going up and down based on how fast the thing is turning. But now we are translating that bicycle wheel to the right. And what this does is it plots out a curve that looks like this. But now it's a function of how fast the wheel is turning and how fast the bicycle wheel is moving sideways. And that is our velocity. So we basically have something moving up and down, and then we turn the wheel sideways and we move it from left to right. And as we do that, this plots out a physical distance. And this right here, what would you say that is called? That is called a wave. Now, because this is now a physical distance, we're going to use our Greek letter lambda, that means distance. And this is a wave. And this is now a physical distance, which we measure in meters. Because it's a wave, and it's the length of a wave, any idea what we might call that?
Wavelength.
That would be a wavelength. So lambda is our wavelength. So that is the length of the wave that we have now made. And it is based on the velocity at which we're moving the thing and how fast it's moving up and down. So notice we have per second over here, and we have a per second over here. Well, if we were to divide one by the other, those per seconds would cancel out, and we would end up with a physical distance, which is exactly what we get. So if we have the thing that's generating a sine wave over here on the left, and we have the whole thing moving to the right at a given speed, that creates a wave moving through space at a given speed and a given distance. So what we now have is okay, so what we now have is we have meters per second of velocity, and we have frequency in cycles per second. And if we divide one by the other, we get V divided by F, because with math, we can do things like that. And we get meters per second divided by cycles per second. And the per seconds cancel out. And now we have meters per cycle. And a cycle, again, is one full trip around of the circle. So now we get our wavelength is equal to V divided by F, which is, again, our velocity divided by our frequency. Or we can rewrite this and say our velocity is equal to our frequency times our wavelength. So now what we're going to do with this is move on to the next thing, which is to say, okay, if our velocity is equal to our frequency times our wavelength, we are going to assume, for the sake of argument, that we are dealing with sound waves. Sound waves travel at about 300 meters per second, 300 meters per second at sea level. So we're going to say that our velocity is about 300, and we have a frequency of 300 hertz, which is a musical note. Not an exact musical note, but we're going to say it's like an audio tone. Okay. And that is measured in cycles per second. And this is meters per second. And we can now arrange this to say, what is our wavelength going to be? And it's V divided by F is equal to 300. I really miss my whiteboard pen. I'm going to try to get this thing to work after break or during break. Zoom, I love you, but I don't love you today. And 300 divided by 300? 1 meter. So a sound wave, yeah.
If anybody has their mouse hovered over the screen, I think that's why we're seeing the other names. If they can get their mice off the screen, that would be awesome.
Yeah, I don't
Okay,
know.
I'm gonna move mine over and see if it comes up. Is mine on the screen now? Over the 3?
Yeah.
Okay. What I do is I bring it up here and pull it around so it can be displayed up on my other screen easier, so that way I can see everything. Otherwise, I only see parts of what is there because the screen being displayed is bigger than what I can have on my screen.
Yeah, I don't understand why it's doing this. That's really weird. This is their new collaborative thing, I guess, which they rolled out without telling anyone. So
that's smartboard for you.
Yeah,
regular smartboards do the same thing.
Yeah, I don't want a smart board. I want a dumb board. All right. Okay, so what we have right now is we have sound. By the way, thank you everybody for working with me here. I'm kind of puzzled as to why this is doing what it's doing, but it says we're collaborating on the whiteboard.
Right. Okay, go down over in your lower right-hand corner.
Yep.
You see the plus and the minus there?
Yes.
You can move that to what you're displaying on your screen, and it will shrink or enlarge what you have on your screen.
Okay. Okay.
That's what I just did, and I can see everything you've got up there now.
Okay. Well, I appreciate everybody working with me here. I'm still trying to figure this out because the whiteboard gets really important. And I don't want to collaborate. I just want to present. So yeah, now I have something to do during break. Okay. Let's see. Allow participants to share a whiteboard. No. Huh. Okay. Anyway, so now what we have is we are dealing with sound waves that traveling through air. A sound wave is a pressure wave. It moves at about 300 meters per second, which is pretty fast. It's about 1/5 of a mile every second. And we've said that if we have a note of 300 hertz, which is like something like that, that wave, as it travels through space, will make a sine wave that is 1 meter long from peak to peak or from trough to trough, depending on however you do it. So
for those that are interested, that's about 3 football fields every second.
Yeah. So, but that's the physical length of how much it actually does. That is what the wave would physically look like. Okay, but now what we're going to say is we're going to change our medium. Sound waves have to travel through air or water or some kind of solid medium. And they're pressure waves and they're interesting, but that is not what we are here for. We are here for a different kind of wave. And that kind of wave that we're working with is something called an electromagnetic wave, which, if people think about that term electromagnetic, electric, magnetic, there are actually two parts to an electromagnetic wave. A sound wave, again, is a pressure wave that travels through space. An electromagnetic wave, it has to follow the same rules. V is equal to F lambda. So that's good, at least, except that as an electromagnetic wave travels through space, it has an electric component, which, let's see, E and the, okay, so the electric component would go up and down, and the magnetic component would go, oh, I don't like that color. I selected another one. There we go. Into and out of the page as the wave itself travels in this direction. So unlike a plain old sine wave, it kind of looks like a sine wave, except that as it's moving to the right, it actually has two pieces. One of them is an electric component, which goes like this, up and down. The other one is a magnetic component. The magnetic component is going to be perpendicular to the electric component, which goes like this. As the whole wave is traveling to the right. These are, if you want to understand exactly what these look like, you can hold up your hand, your right hand. It has to be your right hand, not your left hand. The right hand, your thumb is the direction of the electric component. The M is the magnetic component, and that goes with your index finger, and your middle finger points in a third direction, so that if you look at your hand, they're all perpendicular to each other. And it has to be the right hand. The left hand rule doesn't work. This is called the right hand rule. You have E and M and the direction of travel. So at all points in time, as your middle finger is moving in one direction, the electric and magnetic field components always have to be perpendicular to each other based on what your thumb and index finger are doing. So there's actually two pieces to it, but again, it still has to follow the exact same rules. The exact same rules are that V is equal to F times lambda. So what I'm going to do is I'm going to cancel the whiteboard and I'm going to bring this up. Well, now that we have started, and hopefully everybody can see that okay. Hopefully Zoom is not screwing this up too. Can everyone see that okay?
Looks good to me.
Okay. All right. Notice we have a whole bunch of different things with hertz up top and with meters or wavelengths down below. Well, sound waves travel through a medium known as air, or a liquid like water, or a solid like the earth. Electromagnetic waves can travel through empty space. They can also travel through things like water or earth, or nothing for that matter. And as they do so, they move at a certain speed, right? That speed has a name. Notice that we have all the way on the right-hand side, we have very high frequencies. That's actually terahertz. That's trillions of hertz. As we move left, we go down by factors of 10, and we get down to the gigahertz, and then we get to the megahertz, and then we get to the kilohertz. After that, we actually get rid of the kilo altogether, and those wavelengths that are corresponding to those frequencies. Let's take the 3 gigahertz. Notice at 3 gigahertz, we look at the bottom and we see we have a wavelength of 100 millimeters. Let's take a look at 3 megahertz all the way on the left. and see that at 3 megahertz, mega means million, which we're going to get to, that translates to a wavelength of 100 meters long, which is longer than a football field. At 3 million times around of the circle per second, each wave covers over 100 meters in length, which means that whatever's carrying that is moving really, really fast. Now, the trick here is that you'll notice that you have X-rays all the way on the right-hand side, ultraviolet, and then it looks like Roy G. Biv. Everyone recognize the color spectrum there? That's visible light, then infrared, then radio. And what this really means is that infrared, ultraviolet, X-rays, and radio are actually all part of the same electromagnetic spectrum. The only thing that differentiates what we call radio from all the different colors of light, infrared, ultraviolet, X-rays, gamma rays, cosmic rays, is that we can't see radio waves. We can't see infrared waves because our eyes are not designed to do so, which means that if we're trying to pick them up, we have to have some other means to do it. So I'm going to try to share this whiteboard again and hope that it doesn't screw up. No, I don't want that. What the heck?
Got
Insane.
kind of a dumb thing, but have you tried right clicking on the whiteboard?
Yes. And the
Okay.
problem is that I'm doing the whiteboard with the iPad. And I was able to do this with the iPad previously, and now I'm not able to. And in fact, just before class, I actually tested it and it said, do you want to use the new whiteboard or the old whiteboard? And I said the old one. So much for listening to what I want to do. But again, I'll work on that during the break. Okay, so what we have now is we have a wave, which I'll draw. This is generated by something going around a circle, which is causing something or other to move up and down if we turn it on its side, and then taking that whole thing and moving it at a velocity. Now, we said that V is equal to F times lambda, right? That's our equation that relates velocity with frequency and wavelength. And we know that looking at our chart, we saw that if we have a frequency of 3 million hertz, we have a wavelength of 100 meters. So we have 300 million times 100 to get our velocity. So what is 300 million times 100? 300 million.
Would that be 30 billion?
No, 3 million times 100, just 3 times 100. So that's 300 million. We get a velocity of 300 million meters per second. Does anyone know about what that number is?
Speed of light.
Speed of light. Okay, so now we know that electromagnetic waves travel, if there's nothing in the way, at roughly 300 million meters per second, which is the speed of light. Because radio waves are really nothing more than just a different color of light. They're a very low frequency, very long wavelength color of light. So what this now means is we know that if we have any frequency or any wavelength, we can figure out the other one, which is really cool because that leads to, okay, well, if I have, let's say, a frequency of 146 megahertz, I can go through and I can figure out my calculation and I can say that C is equal to F times lambda and put this in a circle like this. and easily remember what my circle looks like. C is equal to F times lambda. And I can go through and redraw this anytime I feel like it, and it makes a little bit of sense. And say that C is, I know, is 300 times 10 to the 6th power, or 300 million. I can replace that by 300, and I can, because we usually have our frequency in megahertz, I can write my frequency in megahertz here, and lambda in meters. And here's a nice circle. So we know whichever one that we don't know, we can cross out like this. Let's say that if I have, if I'm given a wavelength of 1,000 meters, or let's say, a frequency of 100 megahertz, let me erase that. Then I know that I don't know my wavelength. I know that I'm 100 megahertz. So I have a divider bar right here, the little divisor bar, so that I know that the one I don't know, which is the lambda, which is wavelength, is 300 divided by 100, which is what? 3 meters long. 3 meters long. Okay, this has a profound impact because I know that in space, this wave will be this long. Now, what's really important about this too is I know that this is 3 meters long. Well, I also know that a piece of wire that will allow this signal to be made and be launched into space is going to have, and we're going to get to this next, is basically going to have on it, a waveform which looks the same way. That the current distribution on our piece of wire, which is just literally a piece of metal, has to be the same length as the thing that it's launching into space. Well, if it has to be the same length, how long would this piece of wire be?
3 meters.
It'd be 3 meters long. In other words, this actually tells you how big to make a piece of wire so that it can launch a signal into the atmosphere, into space. So what that also says is, okay, well, it has to be 0 at the ends. How long could I also make this? Instead of 3 meters, what could I make it? I could make it half the length, which is 1.5 meters, because it still meets the fact that it's 0 at both ends. And we're going to get to the fact that you can't have current that exists that's not 0 at the end of a piece of wire. We're going to get to that in just a minute. After break, after I try to figure out this whole whiteboard thing. So that means that this 1.5 meters is a wire that is the right size also to launch a signal that has a wavelength of 3 meters. Again, this is very profound. This basically means that this actually defines what our antenna size is supposed to be in order to use a particular frequency. And after a 10-minute break, we're going to hopefully have a whiteboard that functions properly, and we're going to get into the electrical side of things.
Just a clarification, Scott, you went
Yeah.
from V velocity to C.
Yep. C is the speed
same
of light.
thing. Oh, C represents the speed of light.
C is the speed of light. E
Okay.
equals, as in E equals MC squared.
Yep. Okay.
Thanks, Scott.
Yeah, Gary. Yeah, Gary. You're
Oh,
muted.
I just said thanks, Scott.
Oh, Gary, do you have any other thoughts or ideas?
Oh, I just real quick. You talked briefly about audio frequencies and wavelengths, and then there's the frequency and wavelength of light. And make it a little more tangible for people, I thought, well, maybe you should start with one or the other. So people feel like they have a grasp on something real instead of, the abstract concept. And then you can relate one to the other.
Okay. Anybody have any questions before we go to break? Okay, 10 minutes. I'm going to try to get this thing to work.
When you were talking about C in there,
Yeah.
that I was just explaining to a gal that's here with me. C, the speed of light, that's a constant, and that's why it's measured as C.
Okay, who's Heather? Whatever your whatever your system just did, it just was bad. Okay, go ahead, Don.
I was saying that the C in that MC squared, it's a constant, and that's why it's measured as a C for the speed of light.
That's correct. Okay, cool. Well, everybody think of more questions, and we'll be back in hopefully about 8 minutes, and I'll hopefully have this thing working.
Hey, hi. What do you want to eat?
And by the way, you guys can continue to talk if you feel like. Dun, 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 dun. I am still here. I'll leave myself visible.
I do have a question for you, Scott.
Uh-huh.
I've been going through the practice tests and I haven't seen any questions about any of this stuff. I mean, it's good background.
Yep.
But
That's right.
I mean, but there's no questions on this kind of stuff as far as I know.
Not specifically.
I think it'll help the understanding in the later segments of the it's broken up in the app like all the way through what is it, T10 or something like that? Into segments.
Yes.
Yeah, I think it'll help in some of the later ones.
I started it again and it came up the same weird way. I don't understand this at all. Yeah, okay, so my philosophy on teaching this stuff is that my goal is to get people to the point where they actually understand the foundational information, because anybody can memorize stuff. I mean, memorizing stuff, getting to the point of being able to remember enough things to memorize and take an exam, that's kind of on everybody here, right? And the thing about memorization is that, okay, memorization works just fine, but what doesn't necessarily work just fine, as far as I'm concerned, is memorizing something without really understanding why something is true. Yes, you can memorize something all you want.
Oh yeah, no, I'm with you. I'm doing well on all the practice tests and the section tests and all that, but even though I know the answers, I don't necessarily understand them. So I'm glad you're going through it.
Yeah. Well, and here's the other thing too. Okay, I'm going to mute that. So here's the other thing that I know for a fact, that I have actually listened to the audiobook version of the question pool, essentially just going through question by question.
Oh,
and
that is brutal.
but it's 2 hours long.
Wow.
It's 2 hours, right? I've got over 10, which means that, okay, there's more time to talk about stuff here. The question is, what are we going to talk about? So, what we talk about is all the stuff that makes the answers make sense, hopefully.
Yeah, I'm with you. Are you
And-
going to get into building antennas?
Oh yeah, of course,
Sweet.
because that's where it gets fun. And, okay, let me click on this whiteboards thing. Allow participants to share whiteboard. No. Okay.
The
I'm gonna-
last whiteboard we saw, it said it don't belong to you.
Right, but I still, you know what? This is not working. Zoom is broken. Zoom is broken. And the reason Zoom is broken is because I started a whiteboard. I cannot use my pen.
Hey, Scott, I
Yeah.
wonder if you don't, on this break, you don't log out, change your settings, and
Yeah.
then come back in and see if that fixes it.
Yeah, I'm gonna try. I'm
I mean,
gonna
we're
go
all
out.
in here. We all have the password and the code, so it's not going to kick us if you step out for a minute.
Yeah, that's true. Okay.
I would do that. I would quit your Zoom, open Zoom back up, go in and change your settings, and then rejoin and see what happens.
Well, you know, here's the problem that I'm having is that like it seems to be saving whiteboards, right?
Yeah.
And I don't care that it's saving whiteboards. I want to change my whiteboard settings to have it the way I had it previously.
And I'm
And
just wondering if you reboot the app, if that's what fixes it.
Well, I did reboot the app. I mean, it was working fine until I logged out and logged back in.
Mm,
So I don't know what to change.
all right. I don't
Um,
know either because I don't have it on the iPad and I don't present. So
Right. Well, but I mean, I've been doing this for years now, and all of a sudden they come up with something that's all screwed up, and I just wanted to.
I know
Go-
I was in the last class you did.
I know. Yeah. Exactly. See, and even this is screwed up. And this is an old one from an old class.
What's funny is I only see a blank screen and our
Right.
names hovering around on the screen. I don't see anything
Right.
else.
That doesn't make any sense.
But then when you're doing all your drawing and whatnot, I see all of that.
Yeah. It doesn't make any sense. That's why I selected old whiteboards because I knew that it worked. I mean, this is literally 8 o'clock this morning that I did that.
Yeah.
Thanks a lot, Zoom.
I'm just glad that Don has a Dr. Pepper on his desk.
All right. I'm going to log out and log back in.
All right. See you in a minute.